All right, you guys. Today we're talking about the area of circles and the area of sectors of circles. So this is really going to be analogous to what we did with arc length. So let's start. The first thing you need to remember is how to find the area of a circle. So that's the formula is pi r squared, and there's a lot of beauty behind that. If you ever want to look up, I believe there's a 1-minute proof online where somebody rearranges some beads to turn a circle into a triangle, and it's a beautiful little informal proof. But area equals pi r squared is our formula to find the area of a circle. Then remember also what we did with arc length in the last lesson. So the way we viewed arc length is we said, well, the length of an arc is really just a fraction of the total circumference. So if you can find the total circumference either with 2 pi r or pi times diameter, and then you got, say, 1/8 of, or more general terms, maybe you've got 37 degrees out of 360 total, then you have a fraction of the total circumference. You just multiply those, and that's your arc length, right? So written out mathematically here, it's the measure of the arc out of a total of 360, and once you have that fraction of the circle, you say, okay, well, I've got that fraction of the total circumference. So we're going to do the analogous same thing today with area, okay? So the very first thing is, what is a sector of a circle? So a sector of a circle, sorry about that. The sector of a circle is really just like a slice of pie, a slice of cake, a slice of pizza, right? It's just some wedge if you cut from the center outward. So you have 2 radiuses and then an arc enclosing them. So in this drawing right here, this radius PA and this radius PB cut this circle into 2 different sectors. We've got the smaller sector right here, and then we've got the larger sector. I'll do it in a different color on the other side. So it cuts it into 2 sectors. Now, if we say sector PAB, because AB, the arc, always refers to the minor arc, sector PAB will always refer to that kind of minor sector. I don't know if we actually use that exact wording, but because we have the minor arc assumed, sector PAB is always talking about the smaller sector. But remember, if we want to talk about a larger arc, like for example, if we want to refer to the arc from A this way to B, we just need to use a third point, right? So here's another diagram. I just add another point. I add C down here and say, you know what? To get from A to B, go the long way. Go through C. And we're talking about arc ACB now, the major arc. So then we can talk about sector PACB if we wanted to talk about the larger sector. So just some naming conventions to be aware of. It's just an extension of what we did with arcs. Okay. So now that we know a sector is a slice of the pizza, a slice of the pie, we go down here and say, well, how do you find the area of it? Well, all it really comes down to is what fraction of the area, what is the area of the whole circle, right? So you find the entire area of the entire circle, and you go, okay, we did that in like chapter 1, we've got that down. And then what fraction of the whole circle is the pizza slice, right? Is it 1/8 of the whole pizza? Is it a half? Is it 3/16? Right? What fraction of the whole circle are we dealing with? And if we have the whole area and the fraction of the circle, then we simply say, well, the area of my sector is the fraction of the circle. So how many degrees out of 360 total are slices? And then times the whole area of the circle, pi r squared. Right? So what fraction of the whole circle? So mathematically writing it out, we've got the area of a sector is simply the measure of the arc out of 360 total. So that's exactly your fraction of the circle you're talking about. And then times the entire area. Okay, so now let's run through some problems. I'll start with some basic just using the area formula, and then we'll progress into more difficult problems with sectors, okay? So the first ones are, find an exact, I'm going to switch me here, find an exact area. So that's going to be left in something like 2 pi, 6 pi, pi over 3, something with a pi in it. So we're not using a calculator to get an approximate decimal. Okay, so we've got, it says, and then find the area to the nearest 100. So we are going to be actually doing both. Okay, so the formula is area equals pi r squared. So we don't have the radius, we have the diameter, and we know, of course, the diameter goes all the way across, and the radius is exactly half of that, so we got the radius is 8 and 8. So we've got the area is pi 8 squared, or 64 pi. So that's the exact area. If we want to approximate that, I could pull over my calculator and say this is 64 times pi. And we get, oh, that's around, and this says to the nearest hundredth, so 201.06. Now, I use a long decimal of pi to find it to the nearest hundredth. However, you might have used 64 times 3.14, and you might have gotten 200.96. So depending on what you use for your approximate value of pi, you get different approximations. And on a test or exam, I would be really clear what to use as pi, either exact or using 3.14, round to the nearest blank, okay? All right, so that was how we find the area. So what about here where it's given us the area and we want to find the radius? So we still have that same relationship, right? A equals pi r squared. But now instead it's giving us that the area is 154. So we're going to plug that 154 in for area and say that's equal to pi r squared. How do we solve for r squared? Okay, so really common mistake here is people say let's square root both sides. Square root both sides. And you get square root of 154 equals pi r, and then you divide by pi, and that's really close. Those are actually the right two steps in the wrong order. I shouldn't say in the wrong order, you could do it this way. However, the mistake here is when you square root pi r squared, you would get the square root of pi. Pi is a number. Pi is around 3 something. So when you take the square root of that number, you're not just left with the same number, you're left with the square root of it. So yeah, you would get r, and you could just divide, but you'd be dividing by the square root of pi. Okay, so that's a common mistake. It's analogous to if we had 2x squared equals 9. You could not take the square root of both sides and get 3 equals 2x. You would get 3 equals the square root of 2 times x, because the square root would apply to both of those. So anyways, that was a separate note. So back to this problem. Instead, before we square root, an easier approach, or maybe a better approach, would be to divide by the number. Okay, because really this is analogous to saying 10 equals 5x squared. So we divide by the 5 first. Pi is just a number, so we divide by the pi first. And we get r squared equals, and whatever the heck 154 over pi is. Okay, and now if we want to know what the radius is, we would say the radius is, we just take the square root of both sides. We get the radius is the square root of 154 over pi. Now, that is the exact answer. Great. Or you could go over to a calculator and you could say the square root of 154 divided by pi. And that's around, wow, 7.00 to the nearest hundredths. Okay. So either one of the exact answer or the approximate answer, it wasn't clear here which one it preferred. On a test or exam, I would be really clear which I was asking for. Okay, so now let's actually find the area of a sector, okay? So again, the area of a sector in general is going to be equal to what fraction of the circle, right? Fraction of circle, and then times total area. Okay, that's our general formula there. And so we've got what fraction of the circle, and in this one it says find the area of both sectors. So let's just find the area of the red sector first. So this sector here, that's 60 degrees out of a total of 360 degrees. And then times the total area of this is pi r squared, or pi 10 squared. So reducing this fraction, it looks like the red arc is 1/6 of our circle, and the entire area of the circle is 100 pi. So I just want to star this. I'll come back to this, but we can go ahead and simplify this by putting this over 1. Now we're multiplying two fractions. A 2 goes into both of these, so that becomes a 50 and a 3. So multiplying those, we get 50 pi on top over 3. And that's our exact answer for the area of, and we could either say the red arc or more clearly, or I mean the red sector, or we could say the area of sector FED. Okay, now over here on the other side, I'll use a different color here. Let's go with purple. I'm going to say, what's the rest of it? Now we could go back to the formula, or I could notice that we've got 1/6 of our circle in the red arc. So what's the rest of the circle? The rest of the circle is 5/6 of the circle of total radius 100 pi. Now, you don't have to go there. You could go back to the formula and say, well, left over I have 300 degrees for the rest of the circle out of a total of 360 degrees times pi, and then the radius is still 10, so pi 10 squared. But that simplifies down to be the rest of this fraction, right? Out of 1, 1/6 went to the red arc, and the rest, 5/6, went to the blue. So we have 5/6 of 100. Again, I could simplify this, so 2 comes out of both. So 50 times 50, that's 250 pi over 3. And this is the area of, and then I'm going to call this sector. And notice I can't use 3 letters anymore because that would imply the short arc. So I have to say, I'm talking about the arc E to G to D. So I'm talking about sector FEGD. Okay. So use the diagram to find the indicated measure. So in the first one, it's saying find the area. So this is just like up above, except there's a decimal here. So the area of this is, we want to find the area of circle M. This is different. So we want to find the area of the whole circle. Okay, so we got 2 ways to look at this. We could just use our formula, which says the area of sector equals, and then what fraction of the circle, so this is the fraction we have, which in this case is 165 over 360 times total area, and we could call that x. That's what we're trying to solve for. Another view I didn't mention above, analogous to what we did in the last lesson, is you could look at the fraction of area is equal to fraction of degrees. And what I mean by that is, proportionally, if you have 3/4 of the degrees in your circle, 270 out of 360, then you have the same fraction of the area. You've got 3/4 of the area. So you could set this up as a proportion, where you have the area of sector out of area of circle equals the measure of your arc out of 360 degrees, right? You could, that's an alternate way to set this up. So I could have just set this up as area of sector out of whole equals 165 over 360. I'm not going to do that. I just want to show you that. Okay, so we've got 38.51 equals, I could at least reduce 165 by, let's see, by 5. So that gives me 33 over 72. A 3 still goes into both of those, so I've got 11 over 24. Okay, so I've got 38.51 equals 11/24. That's just the simplified fraction of the total area. So now all I have to do is solve this. So I could do it in one step by just, this is an analogous problem to 2x equals 6. You just divide by the number next to x. Here, the number we're dividing by would be an entire fraction, or dividing by 11 over 24 is the same thing as multiplying by 24 over 11. So multiply by 24 over 11, and there's your answer. So x equals, and then we're just going to figure out what that is. So I'm going to say over here, 24 divided by 11 times 38.51. And so that comes out to be 84.02. So I'm going to do an approximate. So 84.02. Great. Okay, so now over here it says find the radius of M. So again, I'm going to use my same formula. I'm going to say, okay, so area of sector equals fraction times whole area. So I've got the area of the sector, 12.36, is equal to, the fraction is 89 degrees out of 360 times pi, and then r squared, and we don't know the radius. So this is going to be a little harder numerically, but what we've got here is, I take another color here, what we've got here is this is just an ugly number. So really this, analogously, this is just like the problem of 5 equals 2x squared. Okay, there's an r squared we want to solve for, multiplied by a number equal to a number. The numbers look a little more difficult here, okay? But rather than trying to do this in so many little steps, let's just instead say, let's divide by that whole number. Whatever the heck 89 over 360 times pi is, let's just divide by that whole number. I mean, you can plug it into a calculator, you can get the number, whatever. I mean, look, I can, here, so 89 divided by 360 times, times pi. So it's about 0.759. You could plug it in a calculator and use that decimal. But I'm just going to leave it as is for now. So, whoops. So I'm going to divide both sides by that. 89 over 360 times pi. Okay, so I'm dividing 12.36 by that. So what I get is, going back to purple here, I've got r squared equals, and this is, yeah, looks a little ugly, but this is just a number. I just haven't calculated it yet. So 89 over 360 times pi. Okay, and again, that was about 0.75 right there. Okay, so now if I want to solve this, I have r squared, so I just square root it. So what I get is r is around, and I'm just going to plug that whole thing in right there. So I've got 12.36 all divided by 89 over 360 times pi, and then I'm going to take the entire square root of that thing. There we go. So we've got 3.989, and I did not round until the end of the problem, so 3.989. And depending on what they wanted you to round to, that would be maybe around 3.99 if they wanted it to the nearest hundredth. Perfect, okay? Let's do just a couple last problems here with composite shapes. So find the area of the shaded region. So I'm going to look at this. Let's see. So I know, I'm going to go pink here. I know that I can assume things are tangent when they look tangent. So tangents to a circle form right angles. So this is a rectangle at least. So opposite sides, 6, 6. Oh my gosh, this is actually a square. That's great. Okay, if the diameter is 6, then the radius of all these circles is 3. And so what I've really got is I've got the area of a square, and I'm taking away half of this circle and half of the same circle. So really I'm just subtracting the area of an entire circle. This would be the same as if I drew that square and then took out the circle and said, what's the area of all this? Right, just rearranging. We're taking out 2 halves of the circle from that square. So this is the area of that square, which is 6 times 6, minus the area of the circle, which is pi r squared. So I get 36 minus 9 pi. That would be the area here. Cool problem, okay? So 18 says find the area of this. So I noticed that the top side and the bottom side are parallel, and the opposite sides do not appear to be parallel. So this is at least a trapezoid. Maybe it was not drawn to scale, and this is a parallelogram or so. but that formula that finds the area of a trapezoid would actually work for anything with more parallel sides or right angles. So we've got the area equals 1/2 base 1 plus base 2 times height, and that's going to give us the whole area, okay? And then what are we taking out here? Well, we're taking out half of a circle, and I can see that because we have a diameter here. So we're going to take off half a circle. Now I'm going to go ahead and erase this so we can see if we can figure out what the radius of this circle is, okay? So what's going to be the radius of this circle? Oh, I see here. This is clever. At first you're like, well, it doesn't give me anything about this length. It doesn't tell me the leftover. It doesn't tell me the leftover. Seemingly we're stuck. However, we know that this is the mid-segment. And the mid-segment that's parallel to the two bases cuts every side in half, including, sorry about that, including this side and the height. So it's halfway between the bases, or 4 and 4. So the radius of this circle is 4. That's a clever little trick there. So we've got area of the trapezoid minus 1/2 the area of a circle. So the area of the trapezoid is 1/2 base 1 plus base 2 in either order times the height, and then minus 1/2 the area of that circle. So pi 4 squared. So we've got 1/2 of 36 times 8 minus 1/2 of 16 pi. So this is 1/2 of 36 is 18 times 8 minus 8 pi. And so 18 times 8, that's 80 plus 64, so that's 144, I believe. So 144 minus 8 pi. And that's the exact answer. If you want to plug that into a calculator and get an approximate version, that's totally okay. Right, now find the area of the shaded region. A couple more composite shapes here. So this one, it appears to be the area of a circle minus the area of a triangle, if we could find that area. So let's see, it does tell us that this length is 5, and we know that all of the radiuses are the same, and this is a right angle, so this is actually an isosceles right triangle of ratio 1, 1, root 2. So we're just going to have to use a little trig, or at least similar triangles, to find that using our special triangle. So we could say, let's say we're looking for x here, or let's call it r since it is the radius. So r is to 5 as 1 is to root 2. So multiplying by 5 on both sides, we get r equals 5 over root 2. Now, we could simplify that, but since that's not an answer, we don't need to rationalize the denominator until the end of the problem. And because we're doing r squared and multiplying based on height, it might work out to just leave it like that for now. Okay, but at the end of the problem, I would have to rationalize the denominator. So the area of my circle is just pi r squared minus the area of my triangle is 1/2 base times height. So going back to pink here, what do I have? I have pi 5 over root 2 squared minus 1/2. The base of my triangle is 2 of those. And so 2 times 5 over root 2, it's 2 over 1. So the top becomes 10 over root 2. And then times the height, which is 5 over root 2. Okay, so now here we get pi times squaring a fraction. It's top times top, and bottom times bottom, and a square root times itself. The square root cancels out. Minus 1/2, and I'm going to multiply the two fractions. I get 50 over square root of 2 times square root of 2 is 2. And so going back here, I've got, okay, so I've got 25 pi over 2 minus, and then this obviously becomes 25, and so you get minus 25 over 2. So that would be the exact area. If you wanted to factor out 25 over 2, just because there's a 25 over 2 in both, you would get that times pi minus 1. That maybe looks better, but absolutely doesn't matter which way you write it, or whether you give an approximate answer. Okay, two last ones here. area of the shaded region? Well, I can think about sliding these two pizza slices together and making one large slice. Or you could just, since they're vertical angles in the same circle, you could just find the area of one slice and multiply it by 2 since they have the same angle, so the same portion. So let's do that. We got the area of one sector is equal to, and shoot, you know what? We've only got this 109 on this side. So we got 109 here, 109 here, but we don't know what the others are. We do know they're equal, so let's call it x. So off to the side here, I'm going to say, okay, well, 360 minus 109 minus 109. It leaves us with 2x, right? Or just adding them up, they add to 360. So we get, that'd be 51, I think 142 is 2x, so x equals 71. Oh yeah, or we could have done this as a diameter. And just the leftover of 180 is x. So we get 71 degrees out of 360. That's one slice. And then times pi r squared. And then we just multiply it by 2. So whatever that comes out to be, the total area is 2 times that. So the total area is 2 times 71 over 360 times pi times 5.2 squared. Now, since those are decimals and 71 doesn't look like it's going to reduce nicely, I'm just going to go ahead and get an approximate value for that. So I get 2 times 71 over 360 times pi times 5.2 squared, and just turning this into an x for times. Let's see. Wow, that worked out nicely even with my crazy writing. So 33.507 or 33.51. Okay. Lastly here, let's look at this. So we can assume tangents are perpendicular to this. We got to assume here that these are on the same level here. But what we end up getting, I believe, is we could show this as a square. It is 20 by 20, but we would need to know that there are some right angles there. So if we get 20 by 20 by 20, we get that, oh, we do have to assume all of these are concentric. Oh, it does say, it says all the radiuses are the same. Great. So we get that if there's 1, 2, 3, 4 radiuses that span 20, that means one radius is a quarter of that, or 5. And so what we're going to get is we're going to get the area of the big square minus 4 areas of the circle. So we get 20 squared minus 4 times pi 5 squared, or 400 minus 4 times 25 pi, or 400 minus, and then we get 100 pi. Okay, so that would be the area. And that's it for the video. I just wanted to go a little deeper into some more challenging problems there. I know in 28 I skipped a little bit over how we know for sure that's a square, but I hope you enjoyed the video.